The objectives of today's lecture will enable you to understand alkynes, their structure, the nomenclature of alkynes, relative stabilities and their physical properties. Students, first of all, let us look at the structural features of alkynes. The two carbon atoms are sp hybridized, which are linked together by sigma bond by sp-sp overlap. And the two unhybridized p orbitals overlap sideways to form pi bonds. The cloud of the pi bond is present cylindrically, symmetrically about the CC sigma bond. Its geometry is linear, and the rotation about the CC sigma bond does not cause any change in energy and electronic density. Now here you can see the overlap between the two sp hybridized carbon atoms making a sigma bond. The unhybridized 2p orbitals overlap sideways. The overlap occurs between y orbitals and z orbitals to make 2 pi bonds. The sp and s overlap between hydrogen and carbon makes a sigma bond between C and H, similarly on the other side. So this is the structure of an alkyne. This whole electronic density of one sigma bond and 2 pi bonds is symmetrically distributed in the middle between the two carbon atoms. In this structure, students, you can see all the bonds that are made by sp hybridized carbon atom. So a sp hybridized carbon atom makes two bonds. This carbon makes a sigma bond with the other carbon atom and on the other side with a hydrogen atom. So two sigma bonds and 2 pi bonds are made by each sp hybridized carbon atom in an alkyne. Now students, let us start the nomenclature of alkynes and learn some IUPAC rules for naming of alkynes. The first rule says that the parent hydrocarbon or the parent chain is the continuous chain containing the triple bond. Look at these examples. If I select this as my main chain, which comprises of 5 carbon atoms, 1, 2, 3, 4 and 5, but it is excluding my triple bond. So it is not my main chain. Instead, I am going to select this chain which is going to include my triple bond 1, 2, 3 and 4. I am going to select this as my main chain because it contains the triple bond. The second rule is the ending "ane" of the alkane is changed by "ine". Look at the first example. It is propane. But when we are going to have a triple bond, then instead of ANE of the alkane, we are going to change it by YNE. For example, propane to propyne when the triple bond is present. The third rule says the main chain is numbered starting from the terminal carbon nearer to the triple bond. Look at these two examples. I'm always going to start with the side which will give the triple bond the lowest possible number. So I'm going to start from this side so that the triple bond gets the lower number. It is going to give it carbon number 1 if I started numbering from this side. On the other hand, if I would have started numbering it from this side, it will give number 3 to my triple bond. So it is incorrect. The fourth rule says that the triple bond is given the number of the lower carbon atoms attached to the triple bond separated by hyphen. Look at this example. This is the same rule that we studied for alkenes as well. The triple bond is present between carbon number 1 and 2. But in the name, we are going to mention carbon number 1, which is the lower carbon of the triple bond. So the name is 1-butyne, not 2-butyne. It can also be but-1-ine. Another rule says that if 2 or more triple bonds are present in the compound, we have to use prefixes like di for 2 triple bonds and tri for 3 triple bonds and so on. Look at this example which is having 2 triple bonds. So the name is penta-1,3-diene. Why penta? Because the long chain is comprising 5 carbon atoms. The triple bonds are present between carbon number 1 and carbon number 3. And we are using di because we are having 2 triple bonds and the ANE of the alkane is changed by YNE. The name of this compound can also be 1,3-pentadiene because the triple bond is present between carbon number 1 and 2. So we are going to mention the lower number. Similarly, the second triple bond is present between carbon number 3 and 4. Again, we have to mention the lower number. We are using di as a prefix because of these 2 triple bonds. Since students, we have learned the nomenclature of alkenes and alkynes. What if in a chain we are having both alkene and alkyne, means double bond along with a triple bond? Then what we are going to do? Here are some rules which we are going to follow while naming molecules containing both double bond and triple bonds. The suffix "ene" is used to denote the presence of double bond, whereas we use "ine" to denote the presence of triple bond. The suffix "ene" always precedes "ine" while naming such a compound which contains both double bond and triple bond. You will always write the double bond first and after that the triple bond. Even when the double bond is assigned the larger number, means even if the double bond is present at a position which is giving it a larger number, you always have to mention it before alkyne. Look at this example in which you can see a double bond is present between carbon number 1 and 2 and triple bond between carbon number 4 and 5. So it is 1-pentene 4-ine. The position number for the double bond is placed before the name of the parent hydrocarbon. This chain comprises of 5 carbon atoms, so the parent name is pentane. Since it is containing a double bond, so we have changed it from pentane to pentene. The position number of the double bond, this is the double bond, the position is 1. It is placed before the name of the parent hydrocarbon, and the parent hydrocarbon is pentene. And while mentioning the triple bond, we are just going to write its position along with "ine", but it is always going to be present after you have mentioned "ene". The next rule is the position number of triple bond is placed between "ene" and "ine", just as what we learned in the previous example. Look at this example in which we are going to mention the position of the triple bond between "ene" and "ine". Remember students that ENE for alkene is always written with the parent chain. And if the same number would result from each terminal, what do I mean by saying this? If I started numbering from this, it would give 1 to a double bond, and if I would start it from this side, it will give carbon number 1 to my triple bond. So when such a situation arises, then the double bond is given the lower possible number. So I have to start numbering from this side to give the double bond the lower number. So the priority is always given to double bond instead of the triple bond. The next rule is the alkyl groups are indicated by methods that we have already studied in alkanes. Look at this example. Now we have to select the longest chain first, which will contain my triple bond. So this is carbon number 1, 2, 3, 4 and 5. So the parent chain comprises of 5 carbon atoms. Now the two substituents or alkyl groups which are present on the main chain are these two which are present on carbon number 3. So the name of this compound is 3,3-dimethyl because two methyl groups are present on carbon number 3. Pent-1-ine. Pent is the stem name for my long chain. 1 is the position of the triple bond and the triple bond is always written as YNE. The name of this compound can also be written as 3,3-dimethyl 1-pentyne because 1 is the position for the triple bond, pent is the hydrocarbon chain, YNE stands for the triple bond. Now students, let us practice all these rules on some examples. This is the first example. So first of all, select the longest chain. Now we are going to start numbering from carbon number 1 over here. Why? Because if I would have started from this side, it will give lower number to double bond. But if I would have started from the other side, it would have given lower number to the triple bond. But the priority is always given to the double bond. Now you can see that I am having 2 double bonds in this chain and 1 triple bond and an alkyl group substituent on carbon number 4. So we have selected the main chain. We have identified the substituent position. The name of this compound is going to be 4-methyl. We always start with the substituents. The position of the substituent is 4. Therefore, I have written 4-methyl. Now, double bond always precedes the triple bond. Double bonds are present between carbon number 1 and 2. So, I am going to mention carbon number 1. For the next carbon atom which is present between carbon number 3 and 4, the double bond is between carbon number 3 and 4, but I am going to mention carbon number 3 which is the lower number. 1,3-hexa. Why hexa? Because the long chain comprises of 6 carbon atoms. Diene, because of the presence of 2 double bonds, I am using a prefix di, ene for double bonds. 5 is the position of triple bond. Ine stands for the triple bond which is present in this chain. So the name of this compound is 4-methyl 1,3-hexadiene 5-ine. Look at the next example. Let us start with selecting the longest chain. This is my long chain. Why? Because it is going to give lower number to the double bond over here. This is 1, 2, 3, 4 and 5. A substituent is present over here which is an isopropyl group. Now students, always remember that if a substituent isopropyl is given, always connect it to the chain with the second carbon atom, never with the terminal carbon atom. That would be N-propyl. But isopropyl is always connected from the center, second carbon atom. The name of this compound is 3-isopropyl. Why? Because it is a substituent. We always name the substituents first. The substituent is isopropyl group which is present on carbon number 3. 3-isopropyl 1,3-pentadiene. Why? Because the double bond is present between carbon number 1 and 2. So we are going to write 1. The second on 3 and 4. But we are going to write 3. So the name is 3-isopropyl 1,3-pentadiene. Now students, it's time for you to think. Give IUPAC names of the following compounds. The first one is 1,3-butadiene. The second one is 1-butene 3-ine. The third one is 2-heptene 4,6-diene. The third one is 3-hexyne. Students, let us study the relative stability of alkenes and alkynes. Alkynes are more stable as compared to alkenes due to the presence of an extra pi bond. That is why alkynes are less reactive than alkenes. This can be understood if we compare the thermodynamic data of alkynes and alkenes. The delta H for 1-hexyne is 290 kilojoules per mole, while that of hexene is 126 kilojoules per mole. Remember that we are taking same carbon atoms. The only difference is the double bond and the triple bond. So this much energy is required to break the triple bond of hexyne. whereas this much energy is required to break the double bond of alkene. So greater the energy is required, stronger is the bond. So alkynes are more stable as compared to alkenes. If we compare the reactivity order of alkane, alkynes and alkenes, then alkenes are the most reactive. After that, alkynes, and the more stable are alkanes. They are least reactive. Remember that they were called parafines. Now students, let us look at some physical properties of alkynes. Alkynes are non-polar, insoluble in water, but soluble in non-polar solvents, just like other hydrocarbons. They are colorless, odorless except acetylene, which have garlic-like odor. The melting point and boiling point and densities increase with the increasing number of carbon atom, or we can say the molar mass also increases as the number of carbon atom increases. From carbon number 2 to carbon number 4, the physical state is gaseous, whereas from carbon number 5 to 12 are liquids. The higher members are solids at room temperature. This is your homework from today's lecture.